Alright, this is the third video on section 16.2, which is about line integrals. Let's remember what we did in a previous video. So given the vector field on R2, so it's a vector field, so input is xy, and the output is some vector in R2, so it has two components, p and q, which is also written as like this by using ij notation. And suppose you are given a parametric curve on the xy plane, where t is from a to b, and then the line integral of the vector field along the curve c, okay, c is actually the curve given this way, line integral along the curve, which is also written in this way. This is in a way just a notation. So the x component of the vector field comes like this, and the y component is like this. And this is computed in this way. Namely, you basically plug in the parameterization to the vector field you integrate. That means you plug in this x and this y to x and y's here and here. That's what this means. And then you take the dot product with the derivative of r of t, namely you differentiate x and y respectively, and you get the vector, and then you take the dot product. So this whole thing is a scalar. It's a scalar valued function of t, and then you integrate with t from a to b. So that's the way to compute line integral. And then let's just work out one more example in this video, and then I'll talk about a line integral with three variables. So first, let's start with this example. Evaluate integral xy dx plus dy, where c is this. C is the curve on the xy plane, but it's a parabola given by y is equal to x squared. From x is 0, x is 0 to 1, so it's also y is 0 to 1. So C is this curve here. Okay, then now, basically the key point for line integral is to find the right parameterization for the curve you integrate over. But sometimes, depending on the problem, this is sometimes given. But if it's not given, you have to find out what this R of t is. And in this case, what's given is just this. So we have to find out what this parameterization is. What is this? Well, when the curve is given like this, y is equal to something x, like y is equal to f of x, like this. If your curve is given this way, there is a canonical way of parameterizing the curve. Namely, in this case, you just take x is equal to t. So x component is t. And then y component is, in this case, t squared. So that's a way to parameterize a curve like this. And then t is basically the x coordinate. So x is from 0 to 1. So in this case, t is from 0 to 1. Okay, so that's what R of t is. And then by looking at this expression, you can read off what p and q are. P is whatever you have in front of dx, and q is whatever you have in front of dy. But in this case, actually what you have is 1, but usually 1 is omitted. So that means in this case, the vector field f, or f of x to be precise, you integrate over is xy for the x component and 1 for the y component. And then all you have to do is just calculate those. First you plug in the parameterization of t to the vector field you integrate, namely x is t, and y is equal to t squared. So all you have to do is just plug in here to here and here to here. So we have t times t squared, and y is just 1. This is t cubed 1. All right, and then you compute the derivative of r, that's r prime. And that's 1 to t. You just differentiate each of those with t. So, therefore, the given line integral c xy dx plus dy is this one, f of t dot r prime t dt, and from 0 to 1 in this case. But what's this? This is more concretely from 0 1 t cubed 1 dot 1 to t and then dt. And what is this? This is equal to 0 1 t cubed plus 2t and dt. So once you get to this is just an integration with one variable t, and you can calculate this as 5/4. So that's it. So let me just wrap up the key point. Essentially for line integral, like I said before, key point is the parameterization. You have to find the right parameterization. And once you find the parameterization, all you have to do is just plug in to this formula. And then here, for this problem, the curve you integrate is given like y is equal to some function of x. So in general, if you have a curve on the xy plane given by y is equal to f of x, this is x-axis, and then it's from x is a, x is b, and then curve like this, this is parameterized as r of t, where x is t and y of f of t. So this is the canonical way of parameterizing a curve given like this, y is equal to f of x. All right. Now, next, let me talk about line integral of a vector field with 3 variables, namely line integral on a vector field on R3. But essentially the same, because if you look at this formula, like here, in a way this formula can be just generalized to R3 with 3 variables, namely like this. Given f of x, y, z is PQR. So we have 3 components, but those PQRs are functions of x, y, z. So strictly speaking, it's written like this. Like this. Given this and a parametric curve r of t, which is x of t, y of t, z of t. So it's a curve in R3 with starting point is a is equal to t is equal to a, and ending point is t is equal to b. Then the line integral over C of this vector field is given in the same formula, exactly in the same formula. You just plug in the parameterization to the vector field you integrate and take the dot product with the derivative. Okay, then this is a vector and this is a vector because you plug in this to here, you get the vector here. And then if you take the derivative, you just differentiate each component. So this is a vector in R3, and you take the dot product, you get a scalar. So this is just a scalar valued function of t, just function of t. So you just integrate, you can integrate from a to b. But just like before, we often write for this integral as this c p dx plus q dx dy plus r dz. Well, to be more precise, PQR, those are functions of x and x, y, z. So this is written as P of z dx plus q of x, y, z dy plus r of x, y, z dz. Okay, then using this, let's work out an example. Here's an example. Evaluate line integral of x plus y dx plus z squared over 25 dy wait a second, d and x dz, where what is c? The curve c, in this case curve c is the line, well actually line segment from 200 to 345. Okay, let's think about this problem. So basically, the idea is the same as the case of two variables. We just simply have three variables in this case. But anyhow, first of all, the vector field we integrate, f of x, y, z, is what? Well, you can read it off from the whatever you see in front of it, dx, dy, dz, in this case, x plus y, z squared over 25, and x. All right. But then now, like I said, for the case of two variables, the key point is to find out the right parameterization of the curve C for which you want to integrate over. So we need to parameterize. We need to parameterize the curve C, namely the line segment C. But how? Well, here's a way to do it. Think this way. So here's the origin O, and then at t is equal to 0, you are, well, so this starting point is 200. So line segment from 200 to 345. So we are here 200. Here. And then we get to 3, 4, 5. So this is a line segment. This is our C. So we have the position vector here and the position vector here. Then how can you actually parameterize a line going through those 2 points? Well, we know this. This is what we did at the beginning of the semester. So it goes through 200, and then t times the direction vector, but direction vector is this vector here. That's the direction vector like this. Namely, the vector starting from 200, ending with 345. So this is 3, 4, 5 minus 200. And that is equal to 200 plus t times 145 actually. 145. Well, if you combine those, you get 2 plus t, 4t, and 5t. And then, of course, when t is equal to 0, you are here in this case. Indeed, if you plug in, if you plug in t is equal to 0, you get 200. And if t is equal to 1, you get this. Indeed, if you plug in t is equal to 1 here, you get 345. So this is a way to parameterize a line segment. And the t is, so of course t is from 0 to 1. T is 0 to 1. Okay. So after we are done with this, all we have to do is just plug in everything to this formula here. And to use the formula, you have to compute this and this. So f of r of t meaning that you plug in the parameterization to here, and here x is this, y is this, no, z is this. So this is equal to 2t plus 4t, and then 5t squared divided by 25, because z is 5t, and then finally x is 2 plus t. And this is computed as 60, wait a second. I'm sorry, wait a second. Sorry, this is not correct. This is 2 plus, sorry about that. This is 2 plus t plus 4, and this. And then this is equal to 2 plus 5t. And then this is the second component is actually t squared. And then you get 2 plus t. All right. And then the derivative is you just differentiate this, you get 145. So therefore, the upshot is that the given line integral is computed as this dot the derivative that is equal to 0, 1. 2 plus 5t t squared 2 plus t dot 1 4 5 dt, and I is equal to 0 1, and then this is 2 plus 4t plus 4t squared plus 10 plus 5t. Okay, dt. And if you simplify everything, you are supposed to get 0 1 12 plus 90, so 90, okay, what happened? I'm sorry, this is 5, sorry about that, this is 5t, so it's 10t plus 4t squared dt, and then once you get to this, all you need is just calculus 1, and you get this. Okay, so that's the way to compute line integral for a vector field on R3. So either with 3 variables, namely on R3 or R2, like this example, this one, this one. Essentially, the formula is the same. And the key point is to find the right parameterization and compute the derivative, and also stick in the parameterization to the vector field, and you take the dot product and compute the integral. Okay, so that's all I have to say for this video.